All right, so I'm Michael Butkiewicz, and I'm going to introduce our system called Klotski, which is designed to reprioritize web content to improve the user experience of loading websites on your mobile phone. Now, I'm sure you've all had painful experiences of loading slow websites on your phone. And it's especially a problem when you're out traveling, like to a conference like this, and you really need to rely on that mobile phone and that mobile connection to get fast internet access. So to take a look at just how painful this experience can be of mobile web, what we did is we looked at the page load times of the top 200 websites on a PC, a phone on Wi-Fi, and a phone on 4G. And what you can see, if you look at the median load times across these top 200 websites, is that while surfing the web on a PC is obviously very fast and snappy at only 2.5 seconds for the average load time, once you move over to a phone, or especially a phone on a mobile connection like 4G, see that the load times are very slow and very painful, making it a bad user experience. Now, these slow load times are not just bad for the user, but also many different players in the web ecosystem. So if you have annoyed users, they tend to use the web less. If you have less users on the web, that means lost business for various web companies. Now, of course, we're not the first people to look at solving this user experience problem. There's been a wide range of existing solutions that have been proposed and implemented to solve it. So things like compression and caching of web resources, custom formats for websites just for mobile phones, custom protocols like Google SPDY, and just other general improvements like faster networks and improving web browsers in general. And what all these prior solutions focus on is reducing page load time. What I'm going to argue here today is that having this as your sole focus, the sole focus of reducing page load times in order to increase the user experience, is not enough. Now, why do I say this is not enough? Well, year over year, we still see that web page load times are increasing. Now, this is largely due to the demands of the user placed on the websites, which is basically that users want a really rich web experience. Now, this rich web experience comes at the cost of website complexity. That is how many different resources or elements are actually on that website. And it's this increase in web complexity which actually causes the increase in page load time, despite current solutions. Now, not only do users want rich websites, but they also have a following tolerance of how long they're waiting to wait for the website to actually be useful. So here you can see year after year how long they're willing to wait for these websites is falling. So I hope you'll, a little ahead of myself there, I hope you'll agree, based on these situations, that web page load times are still increasing and that user tolerance is falling, that the current approach of just focusing on web page load time is not enough. So given that for the foreseeable future, high page load times are likely to be the norm and not the exception, what can we do to increase the user experience? Well, we think the solution comes from a reformulation of the problem itself. So instead of asking, how do we reduce web page load time, given that web page load times are likely to be high in the foreseeable future, we think that what you should be asking is how can you prioritize the content most important to the user? Now, the reason why this solution works so well is because we already know that users have this brief tolerance window at the beginning of a web page load, this 2 to 4 seconds where they want to start using the website. So what we can do is we can use that brief period of time as a time budget for our optimization and try to push as much high priority resources down to the client within that time budget. Now, our solution, Klotski, does just this. And because our solution is implemented as a web proxy, it actually requires no modifications to either the clients or the web servers. So what does Klotski look like in action? Well, here you can see we've told Klotski that we want it to prioritize within the first 3 seconds as much of the above the fold content, that is the resources at the top of the website, as possible. So on the left, you can see without Klotski of loading the mobile Huffington Post website, and on the right with Klotski. And you can see that Klotski within these first 3 seconds is actually able to reprioritize web content in order to deliver that subset of resources at the top of the page load much faster than without it. So this is a real win for the user experience. So now that you've seen what Klotski can do, let's talk about how it's actually designed and laid out. So here's kind of an idealized view of Klotski. It sits in between the client and the web server. Now, who would actually go and deploy and support Klotski? Well, we feel because it offers such a benefit that there's lots of different players in the web ecosystem who would do this. So you might have a person or a company like Google who wants to deploy this for their mobile users, or even ISPs who may offer this as a free or a paid service for their subscribers. So on the right, you can see the web server, and inside of the web server, there are certain web page resources. Now, these are all the files, the HTML, CSS, JavaScript images that the client needs to download in order to actually render the web page. The way Klotski works is that it has some idea, some a priori knowledge of the website, specifically what types of resources it can expect on the website at any point in time. It also has the idea of a user utility function. Now, this is basically what kind or what types of resources the user finds most important. Now, if it applies this user utility function to its idea of what's on the website, it can actually categorize resources into high importance and low importance, that is high priority and low priority. Now, the goal of Klotski is, despite whatever the ordering of the client requests the resources for the website, Klotski is going to return them to the client in an optimized order. So here you can see that it's reprioritizing these resources to get the most number of high priority resources within that initial load time budget, so the first few seconds of the website load. Now, there's 3 challenges with this system. I'll mention them briefly, then we'll go over in a little more detail. The first challenge is that the content on the website is dynamic, which is that it changes over time. So our view of the website has to change over time, and that this content has certain loading dependencies which have to be respected. The second challenge is that when we're actually choosing what to prioritize, it has to be a very fast algorithm. This is because this prioritization in the algorithm is running in parallel with the actual loading of the website itself. The third challenge is that once we come up with our solution of what subset we want to prioritize, we have to make sure that it's actually going to fit within that initial time budget. So let's go into a little more detail. Now, the first challenge is that content is dynamic in nature, that is, it changes over time and has certain loading dependencies. So I'll give an example of why Klotski needs to have this knowledge about the website. So let's say that there's an image on the website, and this image is loaded by a JavaScript. Now, prioritizing the image by itself is somewhat useless. We can give that image to the client as quickly as possible, but the client doesn't actually know what to do with that image until it gets the JavaScript. Thus, because there's this loading dependency between the image and the JavaScript, we actually have to know that we need to prioritize both and send them in a certain order. Now, the second part of this challenge is that there are certain loading, or that the content is dynamic. So let's assume that this image is actually the headline image for a news site like CNN.com. Now, obviously, over time, that headline image is going to change. It's going to get replaced. Now, because Klotski has this a priori knowledge of the resources, we have to somehow add to that the idea that it's going to change over time, so that when the client requests the website, we can see a new headline image, but still associate it with the old headline images that we already know about and we know how to prioritize. So what we need is some way to encapsulate all of this information about the website, its dependencies, how it changes over time, so that we can gather our a priori knowledge. Now, there's been some work on how to infer and how to store these resource dependencies for websites. Now, the problem with this prior work is that they basically just loaded the website one time, built this dependency structure that you see on the left here of what loads what inside the website. But the problem with this is that the dependencies, like you see here, are not reusable over time. They're going to change because of the dynamic nature of content. So in order to take the static view of a website dependency and make it more dynamic and reusable over time, we base our solution on 2 key observations. The first is that the content in each node of this dependency structure may change over time, like the headline image being replaced day after day. But the structure itself of this dependency structure is actually fairly stable over time. So using this observation, what we do is we load a page repeatedly to generate what we call a fingerprint for that website. Now, the fingerprint is this dependency structure like you see here, but what's stored at every node in the dependency structure is actually a URL pattern. The reason we use this pattern is because it allows us to generalize the URL of any dynamic resources, so that when we see that headline image in the future, although it might be slightly different and have a slightly different URL, we can still recognize, hey, this is the headline image, it goes here in the dependency structure, and we know how to prioritize that. So how do we actually build these URL patterns that we're going to put at every node? Well, let's just assume that we know all the prior URLs that a certain resource has appeared as, right? So while we've seen this headline image change, we've seen that it's had a different URL every time. So if we know this set of prior URLs, all we have to do is somehow generalize it. And what we found out is actually just taking the difference between the set of different URLs and just using regex wildcards, it's actually enough to represent that element and generalize it so that it can be used in the future. Now, why can we use such an easy solution as this, as just using a regex wildcard? Well, we looked at how websites change over several months and over several thousand websites. And what we found is there's actually only 3 real cases for all different websites replacements. So these 3 different cases, maybe not all, but 90% of all the replacements. And each of these 3 cases can actually be handled quickly and accurately by just regex wildcarding. So these 3 cases are a single token in the URL changes, like you see in the example above. Only the URL argument changes, or only the CDN node name in the URL changes. So this whole solution is based on the fact that we know all the prior URLs for a resource, which may change over time. So how do we actually build this set of prior URLs? Well, to do that, we actually have to track the replacement of a resource over time, that is, over multiple page loads. So you have to do something like this. You take 2 loads of a website. You notice that for some resources, the URL stays the same, whereas for other resources, the URL changes. So you actually have to match up between 2 loads of websites the URLs that change for a resource. And we have a couple ways to do this. We either match the position of the 2 resources in the dependency tree structure, or we match on where the resource shows up either on the screen, or if the contents on the screen shift between page loads, where the resource shows up in the source code. So now that we have our dependency structure, which is invariant over time and can be used for future loads, we have to figure out what resources in this subset do we actually want to prioritize. So what we do for this is that we take this dependency structure that we just built up, and we can annotate it with the user utility function to mark resources as being high or low priority. Now, the hard part here is that you can't just select a subset of prioritized resources from the high importance resources. This is because you still have to respect the dependency structure of the website. Like we said before, you can't send the image down before the JavaScript. So the solution here is to actually select the subset by making a cut in this DAG tree, in this DAG structure. Because if you make the cut, you're actually still respecting the dependency structure and the links between the parents and the children. So doing this cut actually reduces to a knapsack problem with dependencies, which is NP hard. Now this is a problem because this needs to be done in parallel with the page load. So what we do is we come up with an approximate solution by using a greedy heuristic, and this gives us a close to optimal solution for the resource selection while still only running in a few milliseconds, which can be done at the very beginning of the page load. So now that we know what subset of resources we want to prioritize, how do we actually do the prioritization? Well, if we know that a resource has a fairly static URL over time, we can actually just push them down to the client as quickly as possible. We actually have in our system a speedy connection between the client and the proxy, which lets us do speedy pushing. Basically fetch the resources really quick at the beginning of the page load and push them down to the client even before the client knew he needed them. This way they're sitting in the client's cache. We know the client's going to want them. He tries to load the resource, and it's basically like it's a cached load. Now, dynamic resources are a lot harder because we don't actually know what the URL of the resource is going to be. We just know that we want to prioritize it. Now the solution is what I've already discussed, where we've actually generalized these URLs with the regex patterns. In this case, when the client requests the resource, we can match it against the regexes we have. We notice that it's a high priority resource, and now we can preempt any ongoing transfers to the client and send down this important resource. So the last challenge that I'll talk about is estimating load times. So let's say our algorithm wants to figure out, okay, I think that I want to send this subset of resources down to the client very quickly. Now we want that subset to actually load within the time budget, which means for a given subset of resources, we have to have some confidence of how long it'll actually take to load on the client. There's a lot of seemingly natural solutions to model this web page load time given a subset of resources, which doesn't actually work. So you can try to do some simple models like the number of bytes in the selected subset, the number of requests that it'll take, the number of resources, things like this. But these are actually all too simple of a model, and they don't capture the effects that browsers have when a web page is actually loaded. There's also, you could think, well, what if we use the information about past loads, right? When we built the dependency structure, we had to load the website a couple times. Maybe we can reuse that. Well, because now we're introducing prioritization and we're changing the order of the loading of objects, the past loads are actually not that useful for predicting the future load. And the last thing is that all of these can't capture the diversity in client conditions. So what happens if the client has a really bad network connection or just has a slow phone? So the solution to our problem rests on identifying that you only really have to model the bottleneck in all of these network transactions. You don't actually have to model everything. Because we're dealing with mobile clients, the bottleneck is obviously again between the proxy and the client, right? This slow 3 or 4G connection. So we can actually save a lot of time in building our model by only focusing on this link of the network transaction. So what we do is we end up building a fluid model simulation. So we model the proxy as a work-conserving scheduler. We make sure that we respect priorities and dependencies. We model the bandwidth as being shared between concurrent transfers because we may be sending more than one resource at a time. And we built in some of the some fixes for some of the subtle issues like how do you preemptively push resources and what about client processing delays? That is, if you give a client a JavaScript resource, they're going to have to take some time to actually process that before they start requesting new things. So all that gets built into the load time estimator. Now, because I introduced these 3 challenges and their solutions, let's see how they actually fit into the whole Klotski architecture. So on the left, you can see the back end of Klotski, which is our fingerprint generator. It goes out and measures websites, builds up this generalized fingerprint. That fingerprint is given to the front end. The resource selection algorithm uses this to actually figure out what resources to prioritize. And to test the prioritization solution, we use our load time estimator to check that it loads within the time budget we select. So now for the experimental results. So the data set for this is we loaded 50 random websites from Alexa's top 200 most popular. And this was done on a smartphone with a 4G connection using Google Chrome as the browser. Now, in addition to these results, there's a lot more in the paper that I'm not going to be able to talk about, like what happens if you use a fast desktop PC with Ethernet, what if you use the full version of website, not just the mobile version like we're doing here. We did a whole user study on user utility preferences of whether users were diverse enough to actually warrant having specific user utility functions, as well as how websites change over time. So here you can see how much Klotski can actually improve the utility of a website in a given load for a given time budget. So on the x-axis, you can see the time budget. That is how good can we do within the first x seconds. The y-axis is the percentage of the site's high utility resources loaded within that time budget. The data shows for all 50 websites, and the box will show the different quartiles for the data. So for example, this line right here shows that the median website was able to load 25% of the above the fold resources in 2 seconds. This is assuming, of course, that the user utility function we're using is to prioritize that top of the page content. So let's add in Klotski. So this is the data of when you actually enable Klotski. And you can see that there's actually, for a 2-second load budget, a 35% utility gain. Now this is great because that's actually a 2x increase over not using Klotski. What that means is in 2 seconds, instead of having only 25% of the above the fold content sent to the user, you actually get 60%. And that's how we got that screenshot that we saw at the beginning of the talk. Now this was for prioritizing for above the fold content. Like I said before, we did a user study and collected lots of different user utility preferences on what they found was important to load first on a web page. Here you can see that across a diverse range of user utility preferences, the utility gains at 2 seconds while using Klotski show very positive results. Even across many different types of user preferences, Klotski is able to improve the experience. So to conclude, mobile web continues to be a pain point for users. And the focus on reducing load time alone is likely insufficient to increase the user experience, or to improve the user experience. So instead of focusing on load time, we focus on dynamic reprioritization of the content. We address 3 key challenges, which is how to represent dependencies and their dynamic nature, how to quickly select resources to prioritize, and how to estimate the load time for those resources. And overall, Klotski is able to greatly improve the user experience across a diverse range of users' preferences. Cool. We're not going to talk about that. That's complicated. Okay.
Hey, I'm Shruti Sanat from HP Labs. I had a question about how did you model user preferences? Is that a user study, or you chose that different patterns of access across websites?
Yeah, so what we did was, so we conducted a user study where we showed the user for several websites, we highlighted different resources on that website. And then we asked the user if they, basically how important do they feel this resource was? That is, how quickly do they want it loaded, and if it was removed from the website, would that impact the website, to try to gauge how much they found that resource important. Then we took those results and we tried to categorize websites into different categories. We then applied those different categories as the user utility function for those different user preferences that you saw before.
Okay, thank you.
Yep.
So this might be a trivial thing, but it occurred to me that you could kill two birds with one stone if you deployed this at the CDN instead of as some independent proxy service, because the CDN is already a server that sits between the user and the real web server, and also some of the disambiguating of different resource URLs is simply different CDN nodes. Well, if the service lived on the CDN, those wouldn't even be a problem. Did you consider this solution? Why isn't it how you deploy it?
So does that assume that all the content comes from, so the user will get all the content for a website through that one CDN?
No, it's just every CDN node will have a copy of this system, and at that node you use the same prioritization to decide which of that content you're going to deliver first.
Yeah, so I mean, if the CDN is basically functioning as this proxy being in between the user and the web server, then it could be deployed there as well.
But in the wild, do users use many different CDNs, or it seems like you were hinting that that's the problem?
So if it's deployed at the CDN, that also, I guess, implies that it can only optimize websites that use that CDN. So certainly if a website wanted to deploy Klotski, well, so if a CDN, let's see. Yeah, basically because it'll only apply to the websites within that CDN. Now, if there's a CDN that has lots of websites and it's used as an advertisement to, hey, host your content here and we'll make it quicker, then yeah, that would be a good solution. I guess we just proposed it as a proxy because it kind of covers everything. There's shouldn't be any special cases.
Okay.
Yep.
Herschel, Stanford. So one of the things that seems an assumption here is that 3 seconds or whatever the number was that users expect right now, once they have your thing, then they're going to start expecting a much faster load time, right? Like, so, I mean, I really think, like, if you ran a study, you would see that creates the new norm.
Yeah.
And then you're like, you've created now a cycle where you need to beat yourself, or I don't even know what would happen there. It would be very...
Seems like a good problem to have, though, right?
Yeah, no, it does seem like a good problem, but I think it's likely to happen.
Yeah.
Cool, thanks.
Okay, one more question? Yeah, so one of the things we thought about, so the question was basically, there are probably other uses for this as well, like deprioritizing ads or maybe pop-ups or things that interfere with your enjoyment of the website. So right now, the way we propose this as the user-defined or we somehow infer from the user their utility preference. And in that case, certainly the user probably, if we gave them the option, and actually this is what we saw in the user studies as well, they tended not to prefer ads being loaded first. So one of the other things we were thinking about looking at is kind of combining user utility preferences with website utility preferences, and how do you actually balance those two. But that would actually require input from the websites, and then you start getting more specific to website user attentions, and it gets tricky. But certainly if you gave the option to have a category to deprioritize, like ads, that could be done. Yep. Yeah.